Log on, tune in, find out. Another good idea from Cambridge.
Speaker is Andrew Stewart and from Warwick, and he will continue on the subject of hybrid Monte Carlo.
Thank you. I'd like to thank the organisers for the opportunity to speak here. I'm going to talk about a continuation of what you just heard, but if you didn't hear it, I'll try and present it in a self-contained way in any case, but there will be connections to the previous talk. So let me just try and say, turn the mic on, please. Okay. There will be connections to the previous talk. So let me just try and relate what we saw in the previous talk to what I'm going to talk about. So Chus's talk was concerned with developing Monte Carlo Markov chain methods to sample a probability density function pi, and the analysis was conducted under the assumption that pi had a product structure. So it could be written as a sum, the exponential, the negative of a sum of identical potentials on each coordinate qi, where the qi from 1 to d make up the vector q. What I'm going to talk about looks somewhat different and is much more motivated by applications. So the form of PDF that I'm interested in hand-waving terms, is like this. An exponential of minus 5q minus a quadratic form. Now the connection to what we've just heard about is that if you choose, this quadratic form is going to be defined through a positive definite symmetric operator C, and if you work in an eigenbasis associated with C, this thing here can be written diagonally. So it can be written as a sum of quadratic terms in each coordinate of Q, where the coordinates are chosen with respect to a basis of C. So this part of the probability measure looks very much like the part of the probability measure that we saw in the previous talk, in that, in the right basis, it can be written diagonally. This part, however, is not diagonal and mixes everything up. However, I want to use the diagonal structure. We saw that it was important in the previous talk, and it's also the fact that for many problems that arise in applications, the diagonal structure that you see here dominates the structure which gives you non-diagonal behavior. And as you'll see in a way that I'll make precise, this will be very much related to the fact that for certain partial differential equations of semi-linear form, the linear part of the equation dominates the theory of existence and uniqueness for the PDE. So I will put conditions on phi, which essentially mean that, in a precise sense, this quadratic part of the probability density function dominates. But nonetheless, phi is important in determining the precise structure of pi. So what we saw in the previous talk was that to make any progress with this kind of probability distribution, you have to, the methods that we were studying were based on time integration of a Hamiltonian associated with the potential made up of the sum of these v's, and the time integration was forced to take a time step which was of order dimension to the minus a quarter, and that gave rise to the overall cost of the algorithm of scaling like d to the quarter, following from the idea that to reach time of order 1 in the differential equation, you need to use 1 over h steps, which is d to the quarter. What I want to show in this talk is that if you have this structure, which, as I say, with regard to this part is essentially diagonal, but it's more than diagonal, it's Gaussian. In this case, you can sample the probability distribution in time of order 1. Okay, so that's the goal. And this is joint work with Alex Beskos, who is at University College, Frank Pinsky, who's in physics department in University of Cincinnati, myself, and Chus. I guess they should be the other way around if they're alphabetical. By the way, for those of you that were in the previous talk, I take no responsibility whatsoever for any politically incorrect things that he might have said. He tried to blame it on his co-authors, but I'm not having any of it. Okay, let me give you a simple take-home idea which explains what the philosophy here is a simple one. To develop algorithms that work without a restriction on the time step in terms of dimension, one way of thinking of doing that is to develop algorithms that work when d is infinite. So to work on function space. And I just want to give you a connection with the heat equation which might motivate the way of thinking that underlies this talk. So if I take the heat equation, say with Dirichlet boundary conditions, and let's imagine rather than doing the method of lines where I discretize in space and then in time, I just try and discretize first of all straight off in space. And so I naively try and write down the Euler method, explicit Euler method. That gives me this iteration, and that iteration is ill-posed. And so I can't even make sense of this iteration here on function space. What is the practical implication of that? Well, if I discretize this now in space and go to some finite dimensional approximation of dimension d, the effect of that is that I'll require a restriction, a Courant restriction on the time step in terms of the 1 over d squared, and this comes about because the fact that this is ill-posed comes because this is an unbounded negative definite operator, and this approximation will have largest eigenvalues which grow like d squared, and that gives us this restriction. On the other hand, if I were to write down backward Euler method, that's perfectly well defined on function space. I don't have to discretize. This makes perfectly good sense. I take over the h Laplacian onto this side. I have the inverse of I plus h Laplacian. That's a nice operator, and I can make sense of this iteratively on function space. And as a consequence, there's no restriction on the step when we try and integrate this in terms of dimension. So all I'm going to do in this talk, what underlies it, is exactly that idea, which I think you can understand for the heat equation fairly quickly, applied to the idea of finding sampling methods which work for this second PDF that's written down here. So I'm going to make sense of this probability density function on a Hilbert space, and then I'm going to write down an algorithm which will generalize what we saw in the previous talk, that will have the property that it's defined on the function space and does not and therefore does not require a restriction on the time step h in order to be used. Okay, I'm going to set up first of all some notation then. So I'm going to have a Hilbert space setting. I love this room because I like the blackboards, but every time I get to this board, which is slightly loose for any of you that used it, I always think it's not such a good room after all. This needs to be attached to the wall. So I'm going to have this inner product setting, Hilbert space. I'm going to let C is going to be a positive definite trace class. So it means the sum of its eigenvalues are finite, operator from H to H. And let me introduce some notation for those eigenvalues and eigenfunctions. So the phi j's are the eigenbasis for C, and they're an orthonormal basis for H, so therefore I can expand any function Q in that basis. So I use Qj to denote the coordinates of Q in the basis defined by C, and I will also define Sobolev-like spaces with index S, which are given by the S norm squared is the sum from 1 to infinity, j to the 2 s qj squared. And I will let hs be equal to q's such that this S norm is finite. And finally, I'm going to put some assumptions on the growth of the eigenvalues lambda, which I'll detail in a moment. And I'm going to, using that, make precise what I told you a moment ago, which is that I'm going to assume that this quadratic part dominates phi. So phi we're going to think of as a function from HL, and I'll be precise about L in a moment, to R. And I'm going to have some assumptions which I'll keep up over here. So I want to put these in the same order I have them here. So let me first do the eigenvalues. So I'm going to assume that there exists k bigger than a half and positive and finite c minus and c plus, such that well, morally speaking, these eigenvalues lambda j decay like j to the k. And I'll give you a specific, thank you, example. Thanks. Should I perhaps do the same with this one? I'll give you a specific example of, thank you. I'll give you a specific example of C if you want to be more concrete. K bigger than a half makes the trace class assumption work. Okay, then I'm going to assume that the phi is that there exists an L, which is, and this is crucial to the domination assumption, L which is less than k minus a half, such that phi is a C1 function from HL to R, and then the derivative of phi is Lipschitz in a particular sense. So as a mapping from HL to H minus L, the derivative of phi is Lipschitz. So these may seem rather technical, but what is encoded in the assumptions over there is the idea that the Gaussian part of the measure that comes from this quadratic form dominates in the coordinates that are found from large J. That's roughly what's going on here. Probably not, no. Thanks. And also, okay, there's another thing. This is rather technical. I'll try and explain why it's relevant. For any epsilon positive, there is an M such that phi of q is bounded below by M minus epsilon q L squared. This condition means when you do certain integrations against Gaussian measures on Hilbert space, you need to control certain things and have them integrable. This condition, with the proviso that L is less than k minus a half, means, well, for example, it means that e to the minus phi is integrable against a certain Gaussian measure that I'm going to write down that has covariance operator C. Okay, so those are technical for those of you that want technical, but the summary of this is that it's showing that the Gaussian part controls the non-Gaussian part of this measure. Okay, so let me get rid of the heat equation. So the how to make sense of, so this formula makes no sense in infinite dimensions. If I were to choose C, there is no Lebesgue measure in infinite dimensions, so I can't write this down. What I can do is the following thing. So I can define a Gaussian measure on H, which I'll call pi 0, That's going to have mean 0 and covariance operator C. And that's equivalent. So how do you think about Gaussian measures? Well, in terms of this expansion of Q in the eigenbasis of C, this is equivalent to saying that the QJs are Gaussian with mean 0 and variance lambda j squared, and that they're independent of each other. This is a sense in which there's a connection between the structure we have here and the previous talk, where we had previous talk we had independent and identically distributed. Here they're independent, but they have different distributions. So this is a way to think of a Gaussian measure. You just expand in the eigenbasis of the covariance operator and randomize the coefficients with variance given by the eigenvalues of the covariance operator. Okay, and then what do we mean by this formula in infinite dimensions? Remembering that I want to make sense of it in infinite dimensions because I want to define an algorithm on the Hilbert space, because because then I'll have H independent of dimension. So what makes sense in the infinite dimensional setting is that the ratio of pi and pi 0 is defined. So this is called the Radon-Nikodym derivative between pi and pi 0. What this means is that if I want to calculate an expectation against pi of f of q, that can be calculated as an expectation against the Gaussian measure of e to the minus phi of q f of q. This is just shorthand for that, which is a way of going from computing expectations against this general measure, in expressing them in terms of expectations with respect to a Gaussian. And our objective when we sample a probability density function is to generate enough functions which look as if they come from pi, so that we can compute expectations of this type. For example, we might want to know the mean or some variance around the mean with respect to our probability distribution. And I haven't said this, and there isn't time to go into it, but there are many applications that have this structure here. In fact, I'm on a mission to write down many inverse problems from a Bayesian perspective in this format, and to show that they satisfy these conditions. So here I've made global Lipschitz, and these things can be weakened. But this structure with conditions of this type occurs in many cases. Okay, so in finite dimensions, what does what I've just said mean? So in finite dimensions, the measure that I've just written down is the one that I'll try and always do the finite dimensions in yellow. It's the one that has this pi up here as density. So the PDF would be exactly pi of q, which is e to the minus phi of q. Because in finite dimensions, we can just take the Gaussian part of the density up and stick it here and get the PDF for the non-Gaussian density pi. So the problem in infinite dimensions, just to explain to you what all the mathematics is about, why I've explained to you, I hope, why I want to define the algorithm on the Hilbert space, because it gives rise to algorithms without a time step restriction. But mathematically what's difficult is that this thing here is almost surely infinite. It's infinite almost surely with respect to the Gaussian measure that I've written down. So that's a generic property of Gaussian measures in infinite dimensions. So the quantity that you'd like to write down as e to the minus a half, that being the density, is infinite. And that's true with respect to pi 0 or pi, in fact. So that's the technical difficulty that we need to overcome. And that, if you remember Chus's talk, the idea that underlies hybrid Monte Carlo, which is the subject of my talk as well, is to integrate a Hamiltonian found from taking this potential, adding to it a kinetic energy, and integrating it with random data. And the fact that this is infinite means that the energy for that Hamiltonian formally will be infinite. So we have to be careful when we try and make sense of hybrid Monte Carlo. Okay, so that was my introduction. So now I want to talk to you about extending the phase space so that we can use Hamiltonian mechanics. That was section 1, although I never wrote it. So we had a nice talk this morning from Christian Lubeck, and one of the things he said was how numerical analysis is sometimes useful for proving things in analysis as well as conversely, and there's something similar to that here. So I'm going to derive for you a partial differential equation of Hamiltonian type, which is invariant with respect to an e to the minus h, in a sense I'll make precise. And in doing that, we basically use numerical analysis, approximate in finite dimensions, and pass to the limit, precisely because of this quantity being infinite. But in any finite dimensional approximation, this is finite, and so we can use numerical analysis and pass to the limit to obtain the result that I'm now heading towards. So I'm going to extend the phase space in the following way. I'm going to extend pi 0 from q alone to q and a momentum p. And I'm going to make the momentum Gaussian with covariance operator, which is a mass operator. Okay? And then I'm going to extend pi to q and p in the same way that we do it here, just through e to the minus 5q. And then let me go to the finite dimensional setting and link with the previous talk. So there's a Hamiltonian underlying this, and that would, if we define h of q and p to be a half p m inverse p, half q c inverse q plus 5q. And if we then define, well, with that definition, if we were in finite dimensions, then pi of q and p would be proportional to e to the minus h. And this maybe should be proportional. And the basic idea that underlies the last talk and this talk, and underlies the idea of hybrid Monte Carlo, which goes back to 1987 and the paper of Duane et al. That Juice mentioned, the basic idea is that if you write down Hamilton's equations for this Hamiltonian, it preserves any density which is a function of the Hamiltonian, and you see that from the Liouville equation. In particular, it preserves e to the minus h. And furthermore, the property that is then exploited is that the marginal of pi of q, where we pi of q and p, where we integrate p out, is then proportional to the thing we're actually interested in, which is this pi up here. So if I was really being nice to you, I'd have different pi's here to distinguish the extended phase space from the original phase space. And we do, in the paper, have larger pi's. Just in case anyone reads the paper, we have larger pi's and smaller pi's, but I can't do that on the blackboard. So in hand-waving terms, I would like to write down Hamiltonian mechanics for this h in infinite dimensions under these conditions. And the problem that we're going to encounter is the same problem that I've written down here. So in infinite dimensions, this quadratic form is infinite, and so too is the quadratic form associated with p. Okay, so that's at the back of should be at the back of our minds about what's difficult. Let me give you an example to have for C. So I don't want to give the impression that this topic is all to do with stochastic analysis. These kind of inverse problems where you have to sample pi in this form arise ubiquitously in statistics. Here this part will be a Gaussian prior, and this will be the log likelihood that comes from data. So there's nothing specific about these problems that relates to stochastic analysis. But the simplest example of C that I want to give in this talk, however, does come from stochastic analysis and comes from what's called Brownian bridge. And it's just a useful example to have in your mind. So this is pi 0 for Brownian bridge. It just gives you an explicit example so you can understand what some of the difficulties are in what we're about to do. So Brownian bridge is just Brownian motion conditioned to start at 0 and end at 0. And we'll do it on a unit interval. So for that operator, for that, that's a Gaussian measure, and it's a Gaussian measure on, you can say, for example, you can view it as a Gaussian measure on L2 of the interval I. And C inverse is minus d2 by dx squared, and the domain of C inverse, it's the Laplacian, negative Laplacian with Dirichlet boundary conditions. So this operator C is a differential operator. So what I'm saying to you when I say this statement down here, in the context of that example, if C is a second order differential operator, then this is the H1 norm squared. And I'm telling you when I write that this is infinite, that if you take a Brownian motion, or Brownian bridge, same thing, almost surely the H1 norm will be infinite. In fact, for Brownian motion, it's in HS for s less than a half, but nothing above that. So this is to do with the regularity of Gaussian random functions. So that example will be useful as we now try and write down a PDE associated with this H. Are there any questions? I've got a question for myself, which is why I didn't bring a bottle of water to this talk. But
There's water there, and also
I've got an answer to my own question. Thank you.
also got glasses.
No, I don't need glasses. Are there any questions? Okay. So let's write down Hamiltonian mechanics. And let me do it first of all. Well, let me just do it as you would for this Hamiltonian. First of all, in terms of P and Q. So for this Hamiltonian, what do I get? I have d2q is n inverse P, and dt, sorry, not d2q, dtq, and dtp is minus C inverse Q minus the derivative phi of Q. And because it's convenient, I'm going to rewrite this in terms of the velocity variable, v, which is n inverse P, from which I get dtq is v, and I get P is nv, so I have m dtv is minus C inverse, which remember you can think of as a second order differential operator in the example, P phi Q. And I'll call this system written in terms of V and Q star. Okay, so that, let's write it also because it might be instructive. Let's write it in terms of a second order equation. So you see that it looks like a second order equation, which is a wave equation type in the case of this example, where C is a second order differential operator in space, second order in time, mass operator, and here a nonlinear term, which is controlled by the linear parts in some sense. Okay, that's the basic equation. And what we like is that e to the minus h be invariant for that equation. But h is almost surely infinite. So what we really mean is not that e to the minus h is invariant, but that the measure pi, defined in this way, is an invariant measure for this equation. And that's certainly true in finite dimensions for any m. So let's go back to finite dimensions. Let me write down what I want to say in that case. So in finite dimensions, for any m, well, for any positive definite symmetric m, we have that pi of qp, which is e to the minus h of qp, is preserved by star. So that is because for any Hamiltonian system, given a smoothness, if you write down the Liouville equation, because the vector field on the right-hand side of this equation or that equation is divergence-free, if you play with the Liouville equation, you see that any density that depends only on h does not change under Liouville evolution. So this will be true in finite dimensions, and what this implies, and this is how hybrid Monte Carlo works, is that if we marginalize this, we integrate out p, then we get the measure we're interested in, which is pi of q, and this is preserved by star, provided we choose the momentum according to the Gaussian measure that you get by exponentiating the negative of this quadratic form in p. Okay, because that's if you look at the e to the minus h, because it's a separable Hamiltonian, that means that the probability density corresponds to p and q being independent. So and the independent part of p is just e to the minus quadratic form, so it's Gaussian. And because it's preserved, e to the minus h is preserved, if I integrate out the Gaussian part, I get the measure on coordinates that I'm interested in. So this is preserved by star if we choose the initial momentum to have covariance, a Gaussian with covariance operator m. That means the initial velocity, and I would like to write it in terms of velocity for reasons that will become clear, has to be chosen from a Gaussian which has mean 0 and covariance operator m inverse. Okay, so everything I've written there is true for arbitrary m. But let's look at infinite dimensions. And let's look at our example. Let's try and look at the example and choose m is equal to the identity, which might be a reasonable starting point. If you do that, this equation becomes d2q minus d2x q is minus d phi of q. So this is a nonlinear wave equation of maybe Klein-Gordon type, Sine-Gordon type, whatever, depending on how you choose your potential phi, but it's a semi-linear wave equation. Okay? And what's difficult about this wave equation is that under the assumptions I've written here, if m is the identity in the infinite dimensional context, that means that you're choosing the velocity, the initial velocity for this. I've written something incorrectly here, sorry. This should have been the initial velocity. We're choosing the initial velocity to be something with covariance operator the identity. That means that the velocity is white noise. So the initial condition for this equation would be a white noise, which is not in L2. So to try and, if one were to try and make sense of hybrid Monte Carlo for arbitrary mass matrices, you see that you run into the difficulties of making sense of semi-linear wave equations with very rough initial data. So I'm not saying that can't be done. It's conceivable that one might develop a theory, but it would be difficult, and it's not clear what the outcome would be. However, as I'm going to show you, there are choices of M for which this equation is a nice equation, and for which one can prove invariance of the measure pi. Okay, so that's the next point. So let me move to that point now.
What does it mean for pi of q to be preserved by star? Pi is not a function of q and
Okay, sorry, I've been a bit loose here and I will be more precise. But let me say it in words. What I mean is, so this is an equation on Q and V, or Q and P, whichever you like. So let's talk about it as an equation on Q and V. If you imagine the following Markov chain on Q, randomize the velocity or momentum, flow the equation, and project back onto Q. That gives a Markov chain on Q, which I'll write down in a few moments. So it's the Markov chain that you get when you view the random momentum as an injection of noise. You flow from whatever Q you're currently at, and then you look at the Q coordinate only. That, because this is preserved on QP space, the Markov chain I've just described preserves the marginal on Q space. That's the basic idea of hybrid Monte Carlo. So I'll write that Markov chain down in a minute. Thank you.
Another question.
Yeah.
So you have defined Gaussians on Hilbert space. You use trace class operators.
Mm-hmm.
So this would exclude the identity.
That's true. So this thing, if you want to make sense of this as a Gaussian measure, you have to do it on negative spaces. H, let's think of another parameter, and alpha will have to be bigger than a half. So it will be trace class on that space. But that whole thing of making sense of white noise is, so that's something that's well understood in a Gaussian measure. So that you can deal with, but then propagating that kind of initial condition through the PDE, that's where the real hard thing is. Okay, so let me take M is C inverse, and let's proceed on that assumption. So why is this a good thing to do? So what we're doing here is, let me just write this H in terms of Q and V, the positions and the velocities. So in terms of the velocities, the quadratic form is, as you all know, I'm sure, written in this form instead of M inverse M, and Q here, and phi of Q here. So what we're about to do, excuse me, is choose M to be C inverse. So in hand waving terms, that corresponds to saying that the velocities are on the same scale as, with respect to the Gaussian part of this measure, are on the same scale as the positions. So we're setting up the measure so that the randomness that we're going to inject into the system through the velocities scales with the index J in the same way that the randomness on Q scales with J. And that's a natural thing to do. If you don't do that, then if you think of the uncoupled case with no phi, then there will be, through mixing of momentum and energy, you will transfer possibly large values of velocity will transfer into large values of Q where they should not do so. On the other hand, if you choose this scaling, the velocity without the coupling phi, the velocities and the positions are on the same scale, and that's natural. Everything gets mixed up by phi, but we have some control on that through these assumptions. Okay, so the equation now looks like something that's very nice. It's just a harmonic oscillator, and then on the right-hand side we have the inverse, C, which is a compact operator, acting on the derivative of phi. So that comes from putting m is C inverse in this equation and applying C to both sides. So this is a semi-linear PDE, if you like, but a very straightforward one, and one to which, because the nice properties of the linear part, you can easily develop an existence and uniqueness theory without any problem whatsoever. So let me tell you then the basic theorem about this. So I will assume m is C inverse from now on. So what I've told you is that there are mathematical difficulties if m equals the identity, and they would be related to studying semi-linear wave equations with white noise data. What I'm now telling you is that with this specific choice of m is C inverse, we can develop a nice theory. I don't have a statement to make about what happens for other choices of m, but this is certainly the most parsimonious choice. It's conceivable that there are other ones that would work, but they would not be natural. This is very natural, and it's natural for the reasons I just gave about putting the velocity on the same scale as the positions. So I need one more piece of notation. So let me let psi t, which will map on q and velocity coordinates, be the solution operator for star. Star being the equation written in terms of q and v. Then under the conditions I've given, psi t maps HL cross HL into itself and is Lipschitz. The Lipschitz constant will depend on the time interval. It is globally Lipschitz, and it preserves the measure pi qp. So that's now a fully Hilbert space statement. So pi of qp should be interpreted. There's no Lebesgue density. It's the measure pi, whose Radon-Nikodym derivative with respect to the Gaussian measure pi 0 is e to the minus phi.
What is the measure of HL times HL in this measure?
Sorry, say it again.
I mean, one typical problem is that if you take the index L to grow to match,
Yeah.
then you get a set of zero measures.
Yeah, that's right. So thank you. That's a good question. So I have this restriction on L being less than k minus a half, and that's precisely for that reason. So pi 0 of HL cross HL, well, let's write it this way, H alpha cross H alpha is equal to 1 for all alpha less than k minus a half, and it's 0 if I go above. From closed interval k minus a half above, it's 0. So this, that's exactly why this index L is chosen in that way. Thanks. So these are this is a natural space on which to write this down. So as Christian mentioned earlier, one can use numerical analysis to prove things about analysis. I don't think these are hard results. It's just that as far as we could find in the literature, there is nothing that would enable us directly to read off invariance of measures which have density with respect to Gaussian from the Hamiltonian structure in the way one can do in finite dimensions. So the way we prove this is in a straightforward way where we discretize, prove the result in finite dimensions, and then pass to the limit. Okay, so now to what Chris Jones just asked me about. So let's make a bit more precise this preserving of the measure pi. So if I let, I'm going to let p sub q of q and v be projection onto the q coordinate, and then I write down the Markov chain. Qn plus 1 is p sub q, flow the Hamiltonian system starting from Qn, and randomize the velocity e to n, and e to n is Gaussian from n0c. So that gives a Markov. So this is a Markov chain. It's this is maybe, depend on your perspective, this is either obscure or clear. What it says is take the wave equation, randomize the velocities from this Gaussian for a fixed initial condition Qn, and when you get to the end, project back onto the position coordinates. That gives you a Markov chain. Sorry. M is C inverse, and so the velocity has covariance operator, which is M inverse, and then
not momentum.
Exactly.
I'm sorry.
No, it's all right. It's for that reason that we introduced the velocity coordinate rather than just working in momentum. The velocity coordinate is nice, and the momentum would be unpleasant. The momentum would be in a very negative Sobolev space. Okay, and then so the corollary, and this is what makes hybrid Monte Carlo fly, is that this Markov chain is invariant for pi of q. So in terms of Chus's talk, this is his maybe third or fourth slide, where he wrote down various methods that were the basis of hybrid of Monte Carlo Markov chain methods: random walk, Mahler, and then hybrid Monte Carlo. And this, we've reached the point of the third slide in his talk. Why have we taken so long? We've taken so long because we're doing this on Hilbert space. But this is now the building block for an algorithm which will be invariant with respect to pi, and will enable us to work with time steps which are independent of dimension, because in fact the algorithm will make sense on the Hilbert space. So what Chus proceeded to do in the rest of his talk, having introduced hybrid Monte Carlo, was to show what happens if you discretize this in time. You add an accept-reject mechanism, and you then, the accept-reject mechanism compensates for the numerical integrator's error, and is such that you still preserve pi. So again, there's a problem now in infinite dimensions. So let me try and highlight to you what that problem is. And then I'll show you how it can be overcome by using a different integrator than Verlet, but a very natural integrator for this one. So, so in finite dimensions, what you would implement would be a proposal Q star, which would be found from a numerical integrator applied to this. So I'll call that psi t h to denote the numerical approximation Qn e to n. And you would then take Qn plus 1 to be equal to Q star with probability alpha, and stay where you are with probability 1 minus alpha. And this alpha, as you will recall from Chus's talk, or if not in any case, is a change in the energy over the integration step. So it's equal to the energy at the beginning, Qn e to n, minus the energy, this is the energy written in terms of position and velocity.
You need an explanation.
Thank you. I'll, let me call this delta H. Thanks. And then the energy at the end of the integration step. And then alpha is 1 min the exponential of delta H. So this idea works provided this integrator is volume preserving and reversible, which the Verlet method is, which was the method we talked about in the previous talk. However, in infinite dimensions, of course, the whole basis of being careful so far is the fact that h is almost surely infinite, and in general, delta h will be almost surely infinite. And in fact, if you think back to the proof part of Choose's talk, you will recall that he controlled the h to be order d to the minus a quarter, precisely because that prevented delta h from going to infinity in what you can think of as a finite truncation of an infinite limit. And we want to get around that. So we need an algorithm for which delta h is finite. So I just finish in the last 2 minutes by showing you how that is done. It's a very straightforward idea. So in words, the idea is that you should integrate the Gaussian part of the problem exactly. And that's a general take-home message about all measures of the type I'm interested in here, which are defined as a change of measure from Gaussian. You can be quite clever with the Gaussian part, because you know a lot about it. And if you build that into the algorithms, you can gain efficiency at the expense of very little work. So focus on our equation written in this form with, remember, m is C inverse. So we have this equation. And I'm going to, so the operator split for Verlet would be to either set to compose with a Strang splitting this 0 with that 0, but rather we're going to compose the operator that you get from the linear part with the operator that you get from just the nonlinear part. So the linear part is just this oscillator, and the nonlinear part is this. I'll call this psi 1 h and this psi 2 h, and then we can do a Strang splitting, if you like, and create a one-step map psi h from these by the usual composition. So this is just as you would create Verlet by composing two maps of this type, but this is a different splitting from Verlet, splitting the linear part and the nonlinear part. So this psi 2 is just a rotation, and this is the nonlinear kick, which comes from the change of measure phi, or its derivative. And then what I call psi th up there is just this composed with itself t over h times. Okay, and the important point that makes the whole story fly is that theorem with this integrator plus, so for plus delta h is almost surely finite. And for any h t positive. So there's no restriction on the time step in terms of dimension. Indeed, we can. This is true on the Hilbert space, and so the whole program of hybrid Monte Carlo transfers to this, to the infinite dimensional analog of this setting here. Okay, so just to conclude, the purpose of doing everything in infinite dimensions, it's a transferable idea that, as I showed you with the heat equation, underlies much of numerical analysis. If you can do algorithms in infinite dimensions, they will tend to be efficient when you discretize them, because they won't have a degeneration as you refine any finite dimensional approximation. So it's worthwhile investing in the development of algorithms that work in the function space setting. And then in terms of the methodology, we've carried this out for hybrid Monte Carlo here. You can do it for other things like the Mahler algorithm. And what I've shown you here is numerical analysis has played a role in two ways. Firstly, we proved the invariance of the measure using finite dimensional approximation and passing to the limit. So numerical analysis was useful to us there in proving invariance of the relevant measure on Hilbert space. And secondly, the ideas from numerical analysis and geometric integration have been of crucial importance in constructing the right integrator, which enabled us to prove that energy changes are almost surely finite. And the key idea is getting the Gaussian part of the problem exact and gives you this result here. Okay, so thank you for your attention.
I'm not really expert on these things, and it's a very beautiful presentation. However, a while ago, I thought that people who basically trying to push into Monte Carlo said Monte Carlo is an efficient way to compute PDEs. Namely, if you have a Laplacian of u equals to something in very high dimension, 10-dimensional Laplacian, you resort to do like basically Monte Carlo to compute the PDEs. Now I see that you'd like to do the opposite in some sense. Instead of doing the Monte Carlo, you would like to use PDEs to simulate the Monte Carlo. Am I getting it correctly, or?
No, that's true. And
So basically now, on one hand, we have PDEs, you go to Monte Carlo, now your Monte Carlo got PDEs. So which is better, chicken or the egg, or whatever? I don't know.
There's no answer to the question at the level of generality that you've asked it, but you're quite right that historically Monte Carlo methods were used and remain used directly to approximate PDEs. It's also true that in this talk I used ideas from PDEs to construct Monte Carlo Markov chain. Both of those will have their place, but I can't give a generic answer to the question.
Further questions? And let's thank Andrew
Thanks.
for this very clear.